Swayam Prabha. Digital India. Educated India.
Okay, welcome back. So, we were talking about necessary conditions for constraint minimization with two variables we discussed. Now, we want to discuss the case of several variables, whether there is the n variables. So, we have let us say a problem that we want to say minimize with respect to, when I put x over bar, that I mean that there is a vector x1, x2, xn. So, f is a function of all of those, and then we have a vector of constraints. So, when I put h, I have h1, h2, h3 up to hm, and it is a function of this x, and that is going to be equal to a 0 vector. Okay. When you have a problem like this, how do we do it? When we had only x1, x2 and we could not eliminate one in terms of the other using the equality constraint, we did that in the perturbation variables. We expressed delta x2 in terms of delta x1 and did that. We will do the similar thing to derive this general necessary condition, that is gradient of the objective function being a linear combination of the gradients of the constraint. Okay. For that, first let us understand that our x now is a n by 1 vector. So, this is n by 1 because we have x1, x2, xn. This one we are going to partition into 2, we are going to partition somewhere into 2 because we have m equality constraints. Again we want m to be less than n, right. So, when we have that, we will be left with n minus m variables. So, we have a reduced search space which we call feasible space. Only in that we have to search, because when you have two variables and equality constraint, eliminated either x1 or x2 in terms of the other, then we had only one variable. Similarly, here when we have n variables and we have m constraints, we can eliminate S1, S2, Sm for example, and left with D1, D2, Dn minus m. We will be having a reduced space. Okay, that is the idea. So, this x now is partitioned into S and D. We use S here because that is like solution variables, we call them. Okay, solution variables. This D are decision variables. They are independent because we can freely specify n minus m variables. Once we know them, using equality constraint we can find the other ones. So, we have partitioned this x into S and D, solution variables S, decision variables D. Okay. Now, we consider Taylor series approximation again. We have f of x star, and then let me change the ink color. Yeah. And then we have this first order term dou f by dou xi, I going from 1 to n, and then this is what we had earlier called delta x. I can call it I now, delta x1, delta x2 and so forth. This is the approximated to first order. Okay. Now, this thing, okay, this one thing is being split into two, that term and then this term. How did it split? Because this delta x star that we had, we are partitioning into delta s star and then delta d star. Okay. All these are vectors. So, I should put a bar there really. Okay. So, this derivative with respect to gradient, with respect to s, this is with respect to d, right. This is how we are doing the first order thing. Now, we say this first order thing should be equal to 0 for f of x star to be a local minimum, that is what we say. But then we want to express delta S star in terms of delta D star, because we have freedom only in n minus m variables, we want to do that. In order to do that, we do the same thing to the equality constraints. We have many. So, we are taking h j, where j goes from 1, 2, 3 up to m, right, as it is shown here, j goes from 1 to m. Each of them we expand, and anyway the 0th order term must be equal to 0 if x star were to be an optimum, because equality constraints must be satisfied, and then we have this first order term that should be equal to 0 to first order, because each equality constraint h 1, h 2 up to h m should be equal to 0 even after perturbation, that should be equal to 0. So, we get an equation such as this for all j equal to 1 to n. So, here j equal to 1 to up to m. Okay. When we have this, we remove that j equal to 1 to m and express it as a matrix form, a compact notation, right. We have gradient of s of the entire h, not h j, but entire h is what we are showing here. When you do this, if you look at the sizes, this will be m by m matrix, and this is m by 1, and this is m by n minus m, and this is n minus m by 1. Overall we will get m by 1, this is also m by 1, this 0 vector will be m by 1, because we have m equality constraints. When we have this, then we can express this delta S star in terms of delta D star, because these are the ones that we can independently vary. This is what we called decision variables, right, D's. Now, we have decision variable perturbation. In order to see if it is minimum or not, we have decision variable perturbations. Okay. In terms of that, we can express the perturbation of the solution variables, right. We eliminated m perturbations, right, and this delta S star that we have here, we can go back and substitute into the first order f approximation over here, right. Then we get some equation which will be the necessary condition. So, now we have done just that. This is what we have delta S star and delta D star. We will substitute for delta S star from the previous slide what we had, right. We have this inverse here of the equality with respect to S, right. We will have this, right. So, now the first order term is going to look something like this. So, we have this anyway has to be the least value for if x star is a minimizer. So, the first order term should be equal to 0, we return that first order term and say that equal to 0, right. Now, we substitute for delta S star, we get something like this. So, what we have here is minus gradient of f with respect to S times gradient of h with respect to S, inverse of that, times delta D h evaluated at that point, and then delta f, all of that we have, right. So, now just like what we had done earlier, first of all this is called the reduced gradient, reduced because it is reduced in the reduced to n minus m variable space. Instead of n variable space, we eliminated m perturbations which we called solution variable perturbations. So, we are left with n minus m, it is called reduced gradient, it is in a smaller space, and here the first order term has to be equal to 0. Okay. That means that think of, let me erase something that we have, think of z, okay, let me see, erase, think of this z, okay, as a function of, so this z here, think of this as a function of D decision variables, okay, then becomes the reduced gradient of that new function rather than f. Now, we have the first order term being equal to 0. Okay. Then we did something, introduce a lambda. What do you define lambda? This whole thing. So, this is our definition of lambda. Okay. We have lambda times this we have decision variables, that is anyway arbitrary. So, first order should be equal to 0, we get this term as it is here. Now, this one, the whole thing is lambda. Okay. Just like we have done 2 variable case, that gives us lambda times this gradient of h which we are inverse, we take it by multiplying again, we get this equal to 0. Okay. And this is what we get over here also. So, if we compare this equation and this equation, this is with respect to s here, this is with respect to d here, just like we had earlier. The way we define lambda gives rise to this one, and the first order perturbation of the reduced gradient gives rise to this. Overall, what we have is that if I put together this first one and second one together, what I get will be this. Okay. So, here with respect to d and d, that is the first order perturbation in the of the reduced gradient vanishing. So, now the way we defined lambda, we got with respect to s, both are identical. This is decision variable, this solution variables. Overall, since x is nothing but decision variable solution put together, we get this thing. So, this is how we get that when we can define a Lagrangian such that it is lambda times h. Basically, what we say here is f plus summation I equal to 1 to m lambda I times h I. Each constraint you add by multiplying with the Lagrange multiplier, okay, linear combination of all the constraints, you get Lagrangian. When you have that Lagrangian, note that it is a lambda 1 by m row vector when we write it like this. Otherwise, I have to put lambda transpose. Now, I make it like a row vector multiplied by, let us say, lambda h. This is 1 by m, this is 1 by m, this is m by 1. So, you will be left with 1 by 1, that is what is, this is 1 by 1, right, it is a scalar. So, what we get is a scalar. Other interpretation what I have written or what is here is that multiplying this, okay. We get the Lagrangian, that becomes unconstrained minimization, right, which is also is going to lead to the same thing that we have here, right, gradient of the objective function plus lambda times gradient of the gradients of the constraints, that are the geometric interpretation. So, gradient of the objective function can be expressed linear combination of the gradients of the constraints, okay. That is what is shown here. Let me erase a few things so you can see this clearly. Okay. So, what we have here is that, okay, for I equal to 1 to n now, okay, we have dou f by dou xi plus summation j equal to 1 to m here, lambda j dou h j by dou xi equal to, that becomes the necessary condition. Okay. Here again we have to count how many equations do you have. Here we have I equal to 1 to n. So, these were n minus m, these were m, put together we get total n. So, we have n equations in n unknowns. Unknowns are x1, x2, x3 up to xn, we have so many equations. So, we are fine, we can solve them. Okay. But then we also have the Lagrange multipliers, right, lambda. So, we have n plus m variables, but then where are the equations? N equations we already saw, necessary conditions. Other m equations are right here, which are the equality constraints. So, we have n plus m variables, n plus m equations, we are fine, we can solve. Okay. That is how we deal with equality constraints, right. And there is geometric interpretation, as we already discussed, that when you have something like this, if there are multiple constraint, let us say I choose a different pen color, let us say that there is this constraint, let us say there is another constraint. So, we are saying that that is not feasible, we can't go there. Similarly, for the red one we cannot be on that side, we have to be below this curve. So, for this f which has a clear unconstrained minimization over there, unconstrained minimum, but unfortunately that is in the infeasible space. This side is a feasible, this is feasible, this side it is infeasible. Okay. So, on the feasible side we have to see where the optimum lies, right. Graphically if you look at it, so I take the green color. So, at this point the gradient objective function will be something like this, okay, because the contour is like that there, that is how the gradient, right, it increases that way. Gradient always points to the most increasing direction. Now, let us at that point put the gradient of this cyan one, which will be like that, okay. And similarly, let us put the gradient of this one here like that. Now, these three arrows, the green one, blue one and red one should sum to 0, that is what is we are saying here. So, the gradient of the objective function, okay, plus lambda 1 times the gradient of the first constraint and lambda 2 times gradient of the second constraint, all these should sum to 0, and that is what this is saying. Okay. The geometric interpretation is what we have on this slide, okay. That is the optimum, right. So, there you cannot make the objective function smaller than what it is here without violating one or the other constraints, that is what means here. So, when I am here, these all my infeasible space, right, all of this my infeasible space, I cannot go there, I have to be on this side. When I move there, objective function value increases or I go into the infeasible space, that is the geometric interpretation of the constraint minimum. So, 2 variables and n variables, okay. Now, let us move on to inequality constraints now. Inequality constraints will be denoted like that, less than or equal to. You can also do greater than equal to, but we stick to the convention of less than or equal to. We have, let us say P inequality constraints, we have M equality here, right, M equality constraints. Now, P inequality constraints like less than or equal to. When you have inequality constraint, there are two possibilities. One is called the active, when G inequality constraint expression is 0 or strictly less than 0, okay, in which case it is inactive. Why is it called inactive? We will see that a little later, but know that there are two ways that are possible for inequality constraint. One is it is active, meaning it is equal to 0 strictly, other is strictly unequal or G is less than 0 at the minimum point, okay. Now, in this case we can write what are called complementarity conditions by writing some variable mu, like lambdas we had for the equality constraints. We can have Lagrange multiplier inequality denoted by mu corresponding this k equal to 1 to p. We have p inequality constraints, we write them like this. The nice thing about this way of writing what is called complementarity is that either that or this equal to 0. When you say mu k times g k equal to 0, it can be satisfied by making mu k 0 or g k 0. Both can be 0, that is a special case, but at least one of them has to be equal to 0. There are two cases. These are called complementarity conditions and this will become useful for us. Okay. So, now when we have, now let us put both back together. When we have equalities and inequalities as shown here, then we write our necessary conditions in this manner. Let us see this carefully. The first one, okay, the first one here, objective function gradient is a linear combination of the equality condition that we already proved, we discussed that. Now, we took the liberty of writing it for the inequalities also by defining these mu's. Here the corresponding multiplier was lambda. Now we have defined mu for inequality constraint. We have taken liberty to write this. The reason is that whenever G is active, meaning a particular inequality constraint is equal to 0 strictly, that becomes like an equality constraint. Whatever arguments we put in here will also apply here. Okay. Now, one might think this is applicable only for those where inequality constraints are active, but then when it is inactive we have this complementarity condition, right. Whenever G, a certain Gk is, let us say, is not equal to 0, it must be definitely less than 0, alright, in which case to satisfy this complementarity condition we must have this mu should be equal to 0, right. When that mu is put, there is no problem, you are only adding something that has no meaning because it is basically 0. We can write it in general, irrespective of a particular inequality constraint is active or inactive, we can add this term. Okay, we can add this term without any problem. Okay. And then we put the feasibility, equality constraint must be satisfied, equality must be satisfied with this less than or equal to, and then we have this complementarity conditions. All of these put together, there are n here, okay, and these are not equations, right, they are inequality, we do not count them, just this part will give me m, but these are equations. See, equality sign is there, there are p. So, total variables and equations, if you see, how many equations? N plus m plus p. Variables are also n plus m plus p because we have n in x, x1, x2, xn, and then m in lambda 1, lambda 2, lambda m, and then p in mu 1, mu 2 up to mu p. So, we have enough equations to solve for the variables, and total here is n plus m plus p. Once again, n is the number of variables, m is the number of equality constraints, and p is the number of inequality constraints. Okay. But we are not done yet. So, this is not the end, we have to say something about, we have used different symbol for Lagrange multipliers associated with inequality constraints called mu. What is the difference between lambda and mu? Is there anything special that forced us to use a different symbol? And there is. Okay. These mu's have this special thing that they have to be non-negative, meaning that they cannot be less than 0. You will see why. Let us take a one variable problem. For inequalities we can take a one variable function, there is no problem. Let us say f of x is like that and g of x is like this. Okay. So, this is f of x, actually g of x is this. Okay. That is g of x, this is f of x. Now, we want to minimize f of x such that g of x is less than or equal to 0, right. That means that this is our feasible space, okay. All this is infeasible, I cannot go to that right side, I have to be on this side, right. Then if you look at f, clearly this is my minimum, constrained minimum, which lies always on the boundary, right. That is why it is called boundary minimum sometimes or boundary optimum. Now, you consider the first order perturbation for this, which is we have denoted this as f prime here. Okay. When I say f prime evaluated at x star times delta x star should be greater than or equal to 0, only then we say f of x star is a minimum, right. Any other perturbation on this side, okay, should give us a quantity for the up to first order should be greater than or equal to 0, right. So, if you look at the g, okay, we have g of x is g x star plus again we put this thing is called g prime. Let me erase what is going to distract us. Yeah. So, we are calling it g prime. So, here we know that g has to be less than or equal to 0. So, g of x star, because that is optimum, that is equal to 0 because that is at that point g is 0, right. So, the first order thing delta x star that should be less than or equal to 0 in order to make this satisfied. So, what we have now is f prime times delta x star is greater than or equal to 0, g prime times delta x star is less than or equal to 0, right. So, now when we consider the necessary condition that we put there, f prime plus mu times g prime equal to 0, we know that this one, okay, let us multiply by delta x star, this equation. So, we know that this has to be greater than or equal to 0 like that, and this has to be less than or equal to 0 because of that, and this should be total should be equal to 0. That makes our mu to be non-negative, meaning that it should be greater than or equal to 0, positive or 0. That is a special condition that comes on this. Okay. So, now we also add that necessary conditions. Now, there are n equations here, there are m equations here, there are p equations there. Additionally, we have this inequalities there and then further inequalities here, that Lagrange multiplier corresponding to inequality constraints have to be non-negative, they have to be positive or 0. Okay. And this actually gives us what we can call, what we condition we have are called KKT conditions. These are something that one should be able to write and explain what they mean even if somebody wakes you up in the middle of the night. Okay. KKT stands for Karush-Kuntakar conditions, 3 people. Sometimes people use only KT conditions, but that is not right, because Karush had proved at least a couple of decades before Kuntakar derived these conditions. Okay. They are called KKT conditions, and we have enough equations and enough variable to solve for the variables, that is x and this lambda and then the mu. Okay. Do not forget this complementarity condition kgk equal to 0, where k goes from 1 to up to p, the number of inequality. Okay. By the way, Karush had done that in a master's thesis at University of Chicago couple of decades before Kuntakar did it at Princeton University. Okay. But there is one little caveat that we need to say, these KKT conditions are applicable only if this constrained qualification is satisfied. Okay. Because when you say necessary conditions, they must be necessary, right, but then sometimes you can construct a special problem where there is clearly a constrained minimum, but that minimum point may not satisfy the KKT conditions as written here, right. In such cases, the constrained qualification test might be not applicable. So, for that reason actually we have to go back to slide number 17 of the previous lecture, which we will quickly go, slide number 20 not 17. So, delta S star we are expressing into delta D star, where we had the inverse of a matrix. Inverse of a matrix cannot be always done, right. What if this matrix, which is m by m matrix here, right, what if it is singular? We cannot do that, right. So, that is constrained qualification. We say that gradients of the equality constraints must be linearly independent, then m by m will not be singular, we can take inverse. Okay. So, that is basically constrained qualification. So, here since we put that caveat here, that KKT conditions are applicable when we have the so called constrained qualification. This is slide number 20. Okay. So, that is important. When you have a problem, please check and ensure that the gradients of the equality constraints are linearly independent, so that when you try to eliminate some variable perturbations in terms of the other, you take inverse, you need that non-singular matrix there, that is satisfied only if they are independent. Okay. That is constraint qualification that we need to remember. So, to summarize, we first considered the 2 variable problem and eliminated one equality constraint. When we cannot do it, we went for the first order approximation, eliminated one perturbation in terms of the other, that gave rise to this concept of Lagrange multiplier, Okay. And then we have the feasible space where the constraints are satisfied. In the case of n variables, we talked about reduced gradients where we eliminated m variable perturbation in terms of the remaining n minus m variables. Then we had m Lagrange multipliers. We just talked about this constraint qualification concept, which simply means that the gradients of the equality constraints must be linearly independent. When you also add in inequality constraints, it is the active inequalities which are g equal to 0. When you have that, those gradients all should be linearly independent along with the rest of the equality constraint gradients. And the sign of the Lagrange multiplier for the inequality constraint, that mu we said should be greater than or equal to 0, mu I, where I goes from 1 to p. We talked of complementary conditions, which basically will have a very nice well, this I k they are all the same, I equal to 1 to p, and what I have written k is also equal to 1 to p. That is, they will tell you whether constraint is active or inactive. Okay. Finally, we had Cauchy-Kontaker conditions that capture all of this. So, this finishes the necessary conditions. Sufficient conditions we can discuss, but then there is a detour. So, we get back to calculus variations in the next lecture. So, basically sufficient condition also exists in the case of n variables, m equality constraints, p inequality constraints. When you read necessary conditions, you can talk about the Hessian like we discussed in the unconstrained minimization. You can talk about the same thing here, but instead of going too much into that, since our course is about this variational methods, we will get back to that in the next lecture. Okay. Thank you.